Hello, welcome to Advanced Composites. Today is the 5th day of the first week of this course, and we have been discussing how to calculate different properties of single layer continuous fiber composites. In last class, we had discussed how to calculate the Young's modulus of these type of composite materials in the longitudinal direction. Today we will discuss about the strength of such composites in the longitudinal direction when they are subjected to longitudinal tensile stresses. So, what we will discuss is tensile strength. Tensile strength in L direction. This is what we want to discuss. So, to illustrate, you have a piece of composite and it is having fibers in the L direction running across the entire length of composite, and this composite is subjected to a tensile load of P. So, remember, we are discussing tensile strength in L direction. We are not talking about compressive strength or shear strength, but tensile strength in L direction. So, what we want to understand is that how do we calculate this ultimate tensile strength. So, ultimate means sigma u and in the L direction. So, how do we find out this value? Now, in our introductory course, we had discussed several scenarios, and based on those scenarios we had discussed that the tensile strength depends on the volume fraction, whether it crosses a minimum threshold or a critical threshold or not. So, first we will discuss those situations, and we will not go into the mathematics of that because the mathematics has already been discussed in the earlier class, but let us consider those scenarios. So, case 1 is when the volume fraction of fiber is less than a particular number, and let us call it V min. So, if the volume fraction of the fiber is less than that of the this V min value, then what happens? As I increase the load on the composite, initially because fibers cannot take a lot of strain, they break, and once they break, whatever load they are carrying, that load gets transferred to the matrix material, and because the matrix material is present in a very large amount, so it has no problem in absorbing that excessive load which it receives because of breakage of fibers, and then I have to pull the composite even further to ensure that the composite fails. So, in this case, the breakage of fiber does not mean that the composite will fail, rather I have to keep on pulling the composite further and further, and only once the matrix fails, then the entire composite fails. So, here what is the failure process? First fiber fails. So, first fibers fail, then they transfer load to matrix, then at higher loads matrix fails and composite fails when matrix fails. Composite fails when matrix fails. So, this is when V equals V min, or the fiber volume fraction is less than V min. The second case is Vf equals V min. In this case, fibers fail, matrix experiences additional load, additional stress, and at this point it breaks immediately due to transfer of load. Okay. It breaks immediately due to transfer of load. So, what happens is fibers fail, and suppose fibers are taking a load of 1000 newtons, that 1000 newtons gets shifted to matrix, and all of a sudden matrix experiences 1000 extra newtons, and it is not strong enough to bear that extra load. So, it also fails at the same time. So, failure of fiber, matrix and composite happens at same load. And the third case is, so this happens for Vf is equal to V min, and also for all volume fractions of fiber when Vf exceeds V min, the same thing happens. Then the third one is Vf is more than V min. It is the same mechanism as above, same as 2, okay, nothing new about that. But in all these cases, cases 1, cases 2, case 3, in all these cases, the overall strength of the composite will still be lesser than the strength of the matrix, because there are very little number of fibers. So, the overall strength of the composite is less than the strength of the matrix, but we want a composite which should be stronger than matrix material, right, and that happens when Vf is greater than another number called V crit. It is a critical volume fraction. So, in this case, same as 2, but strength of composite is more than strength of matrix. Okay. So, if we are designing a composite material, we have to make sure that our volume fraction should exceed, volume fraction for fibers, it should exceed the critical volume fraction. So, the next thing what I am going to do is I am going to provide you these numbers. Okay. So, V crit, critical volume fraction is, if you want to find out what is the critical volume fraction, so that is equal to ultimate tensile strength of matrix minus sigma m underscore, okay, and we will explain what that means, divided by ultimate tensile strength of the fiber minus sigma m under bar. And what is sigma m under bar? This is stress in matrix corresponding failure strain in fiber. What does this mean in plain English? That suppose fiber fails at 1% strain. So, what will be the value of sigma m under bar? You pull a piece of sigma m matrix material, pure matrix material, and subject it to 1% strain and monitor the stress level. That stress is sigma m under bar. Okay. So, that is there, and if V F is equal to or greater than V crit, then the tensile strength of the composite material sigma L. Now, what did we say? Sigma UL is defined as, or it can be calculated by sigma ultimate tensile strength of fiber times volume fraction of the fiber plus 1 minus Vf times sigma m underscore. So, this expression gives us the tensile strength of the composite material if volume fraction of fiber is more than critical value. And for the other case, if it is not the case, then let us also find out what is the value of minimum volume fraction V min, and V min is sigma um minus sigma m underscore, which we have already explained, divided by ultimate tensile strength of fiber plus ultimate tensile strength of matrix minus sigma m bar. And in such a case, the ultimate tensile strength of composite is equal to sigma um times Vm, which is what? Sigma um is ultimate tensile strength of the matrix material. So, these are the two scenarios, and for both these scenarios we have defined the tensile strength of composite in the longitudinal direction. The next thing we will cover, so we have discussed longitudinal modulus and longitudinal strength. The next thing we will discuss is transverse modulus. Transverse modulus. So, just to we will start by illustrating. So, what does transverse modulus mean? That suppose I have a sample of composite material and the fibers are again running like this. So, this is my L direction, that is my T direction. So, here I am interested in finding ET, and in this case it means that I am subjecting my sample to a load P, but this P is aligned with the T direction. Okay. So, ET equals stress in the transverse direction divided by strain in the transverse direction. This is assuming the material is linearly elastic. So, if I plot stress and strain, if it is a straight line, then this is the expression for ET. So, first we will make a coarse model like we developed for longitudinal modulus. So, suppose I have a piece of composite and it has some number of fibers and the remaining part is matrix. So, let us say that I designate this part, all this is fiber. So, this thickness corresponds to volume fraction of the fiber and this thickness corresponds to volume fraction of matrix material. So, when I am looking at it transversely, I am just moving and collecting all the fibers in one side and matrix is in the other side, and I am subjecting it to load P. So, this is one way to get an idea what will be the value of ET. So, in this case the stress in composite will be same as stress in fiber and it will be same as stress in matrix. Okay. Also, when I pull this sample, the overall sample will stretch by some distance delta c, and this stretching will be what? It will be the sum of stretching of fiber plus stretching of matrix. Okay. So, this is expression 1 and this is expression 2. So, from 2 what do we get? We can expand this stretching. So, expansion in the composite is nothing but strain in composite in the transverse direction times the thickness of composite. So, this is my thickness total Tc, this is Tm and this is Tf. Okay. So, delta C is strain in the composite times thickness of the composite, and that equals strain in fiber times thickness of fiber, because that is what delta F is, plus strain in matrix times thickness of matrix. And now what I do is I divide this entire expression by Tc. So, I get epsilon C is equal to epsilon F, and what is Tf over Tc? It is the volume fraction of fiber. So, Vf plus epsilon m, and Tm over Tc is volume fraction of matrix. Now, what is epsilon C? Epsilon C is sigma C divided by Et, right. It is the stress in composite sigma C divided by the transverse modulus of the composite. Epsilon F is sigma F divided by Ef, and so on and so forth. So, I plug these things in this equation. So, I get sigma C by Et is equal to sigma F over Ef Vf plus sigma m over Em Vm. And now we use equation 1, which says that sigma C, sigma F and sigma m are same. So, these guys go away and I am left with is 1 over Et is equal to Vf over Ef, excuse me, plus Vm over Em. This is there. So, this is one expression for transverse modulus using the assumptions listed here in equations 1 and 2. And then once again we ask the question, is does this equation really work? And to find that out, people did experiments, and what they found, that this expression does not work in a large number of cases. It has limited accuracy, and there are several reasons for its inaccuracies, which we will not go into, but they have been discussed in the introductory course. So, people built more sophisticated models, and one model which provides very good results is, I will explain that, and that is known as the Halpin-Tsai model. Halpin-Tsai model. So, I am going to just write down the result directly from there. So, if I have to compute transverse modulus of a unidirectional fibrous composite, then the relation for that using Halpin-Tsai relation is this, that Et over Em equals 1 plus zeta eta times volume fraction of fiber divided by 1 minus eta times Vf, which is again volume fraction of the fiber. And you would ask, what are these things, zeta and eta? So, eta equals Ef over Em minus 1 divided by Ef over Em plus zeta, okay. And zeta, it depends on the type of fiber which we use. So, if it is, its value is 2, if the fiber is circular in cross section or it has a square cross section. But if it is a different cross section, let us say rectangular or elliptical, so in that case it is twice of A over B, okay. And what is A? So, suppose you have, so A is the dimension of cross section aligned to load direction, okay, and B is the other dimension, B is the other dimension. So, this is how you compute the transverse modulus, and this particular relation, the Halpin-Tsai relation, provides fairly good results, which are so good results in the sense that they are fairly consistent with lot of experimental data. So, if we want to quickly compute the transverse modulus of a unidirectional fibrous composite, then if we use this relation, we will be in good hands. So, this is what I wanted to discuss today. Tomorrow we will continue this discussion and we will talk about some other material properties and hopefully close this discussion related to prediction of properties of unidirectional composite materials. Thank you.